Hello, George Notchik here. In this video, I'm going to provide a rigorous proof that if you have a polynomial of nth degree with real coefficients and you happen to find a root to be a complex number, then you're guaranteed that another root is its conjugate, that the solutions to polynomial equations with real coefficients, the roots always occur in complex conjugate pairs. So we can state this in this fashion. If an nth degree polynomial with real coefficients has a complex root z1, then the complex conjugate of z1 is also a root. Stated mathematically, we have it that p of n of z is a polynomial in z of nth order, and we can write it in compact form this way, where we have a sum from k equals 0 to n of ak times the complex number raised to the k power, and the polynomial equation we set equal to 0 to find the roots. Then if z1 satisfies this equation, that is, makes the equation 0, then z1 conjugate substituted into that same equation also gives us 0, and the coefficients are in the real numbers. If the coefficients are allowed to be complex numbers, then this does not hold, because your complex roots don't have to occur in conjugate pairs if you have complex numbers as your coefficients in the polynomial equation. But if your coefficients are real, are members of the real numbers, you're guaranteed that the roots always occur in complex conjugate pairs. You can show this with an example. Suppose that I have this polynomial equation, a third order polynomial equation, z cubed minus 4z plus 46z plus 116. And we set that equal to 0. We want to know what the roots are. There's going to be three roots. Frederick Gauss proved in his PhD thesis that an nth degree polynomial is guaranteed to have n roots. An nth degree polynomial always has the same number of roots as the highest order of power in the equation. So we're guaranteed to have three roots here. And the other thing is if you have an odd order polynomial, one of the roots have to be real, because the roots occur in complex conjugate pairs. So if you have an odd number, that odd number root has to be real. So suppose we find in this equation that z equals to 3 plus j7 satisfies the equation, which it does. Then we're also guaranteed that if z1 satisfies the equation, then z1 conjugate also satisfies the equation. So we find one complex root, then we automatically can write down the other complex root as the conjugate of the root that we just found. So all we have to do now to prove this is to find the last remaining root. And the way we can do that is we can form a factor with z1 and z1 conjugate divided in this equation and see what we have left over. So we can do that. The factor corresponding to z1 will be z minus 3 minus j7. And the factor corresponding to z1 conjugate will be z minus 3 plus j7. So we want to multiply these together to give a second order equation. Then we divide it in here to get the last root. Well, we can do that by forming it this way. I will write it in this fashion. And then I'm going to multiply these two factors together. Well, we have z minus 3 squared this times this, and then z minus 3 times minus j7, z minus 3 plus j7. These cancel because they're conjugates. And then we're left over with minus j7 plus j7 multiplied together. The j's squared gives us a minus 1. Minus minus is a plus, so we have plus 49. So we can expand this out. That's z minus 3 squared. So this gives us z squared, first term squared, times twice the cross product, which would give us minus 6z, and then plus minus 3 squared, which is 9, and then we add 49. So we're left with z squared minus 6z plus 58. So that's the expanded form of the two factors here. So we're going to divide that into the original equation to see what we have left over. Well, we can do that in this fashion. We can write the top equation synthetically. We have 1 minus 4, 46, 116. And then this equation, we have 1 minus 6 and 58. So first off, multiply by z. So we get 1 minus 6, 58. We negate it and add. We get 2 minus 12, 116. Then we can multiply by positive 2. 2 times 1 is 2. 2 times minus 6 is minus 12. 2 times 58 is 116. We negate and add, and we get 0. So z plus 2 is the other remaining factor. So we can write this as z plus 2. And this will equal this equation here if we multiply it out. So the other root is z equals minus 1. So I just did that to show that the complex conjugate also satisfies the equation. So now to prove this theory, or this theorem, we'll first establish a few basics in complex numbers, and then the proof will go rather quickly. It's really going to be a very short proof once we establish a few identities in the complex numbers. Okay, a few preliminaries. The first preliminary is going to be, we're going to look at what happens when we take the conjugate of a number, a complex number, to a power, and the conjugate of the product of complex numbers and the sum of complex numbers. First off is if we have z raised to the power k and we take its conjugate, then this, we can interchange the power and the conjugate. This becomes z conjugate raised to the power k. And we can easily show that by writing z in its polar form or exponential form. So we have z is equal to its magnitude times e raised to j theta, where theta is the angle that's established by the arctangent of the imaginary part divided by the real part. And if this is z, then z conjugate has the same magnitude but the opposite angle. I showed that in an earlier video on manipulating complex numbers. Now, if we take z to the k, we can write this as m e to the j theta raised to the k power, and this becomes m to the k power e to the j k theta. Now if we take the complex conjugate of this, so we have z k conjugate, we take the conjugate of mk e to the j k theta. Well, m to the k is a real number, so its conjugate is just the number back. So this is mk. The conjugate of a real number is just a real number. Like the conjugate of 2 is 2. Conjugate of -7 is -7. There is no imaginary part to a real number. Then if we take the conjugate of this, we take the opposite angle. So we can write the conjugate in that fashion. Now we can pair this as m e to the minus j theta. Using properties of exponents, I can pull the k out. The k gets distributed to the m and to the exponent, so I can write it out. Now this is just z conjugate. So this is z conjugate raised to the k power. So this is the first property of the complex numbers. Okay, now we'll do the next one. The next property is that if I have z1 times z2 and I take its conjugate, then the conjugation distributes through the multiplication. The conjugate of z1 times z2 is z1 conjugate times z2 conjugate. Again, we can write these in exponential form and see what happens. So if z1 is m1 e to the j theta 1 and z2 is m2 e to the j theta 2, we can form the product. z1 z2 is m1 m2 e to the j theta 1 times e to the j theta 2. Using properties of exponents, we can combine the exponents on the base e here. So it's j theta 1 plus theta 2. Now, if I take the conjugate, z1, z2 conjugate, then this becomes m1, m2, and minus the angle, e to the minus j theta 1 plus theta 2. That's the conjugate. Now, I can expand this out. I can put the m1 and m2, and I expand this out. I have e to the minus j theta 1 times e to the minus j theta 2 using properties of exponents. And then I pair it as m1 e to the j theta minus theta 1 times m2 e to the minus j theta 2. So this is z1 conjugate, and by definition that's z2 conjugate. So it's the product. So z1 times z2 conjugate is z1 conjugate times z2 conjugate. So that's the other property we'll be using. Okay, now we'll do a third property. The third property would be if we have the sum of several complex numbers, the conjugates of those numbers, or let's write it this way. Let's say we have the sum of several complex numbers. I'll call them z sub I. And I take the conjugate of that whole sum. Well, the conjugation distributes through. It will be the sum of the conjugates. The conjugate of the sum is equal to the sum of the conjugates. Well, we can look at it this way. The sum, we can write z sub i's as x of I plus j y sub I. or let's call them k's. Let's call it so I don't mix up indices with the unit imaginary. We'll call it zk's. Now, zk can be written as xk plus I or j. I'm mixing up I and j, but remember they mean the same thing. It's the square root of minus 1. So I have xk plus, I've been talking about j, so I'll call it j yk. J, remember, j or I is the square root of minus 1. That's a unit imaginary. I interchange them a lot, because in electrical engineering I talk about it as being j, and mathematicians use I. It just use it interchangeably. Now, so if this is a complex number zk, then the conjugate of zk is just the negative of the imaginary part. Okay, so now if I say look at, let's look at this side here, the summation of zk conjugates will be equal to x of k plus I or j y sub k conjugate. Now, by definition, the conjugate of this can be written in this fashion. This is z times x of k minus j y sub k. I'm just using the definition of conjugate. Zk, the sum of these zk conjugates is the sum of the xk's plus jyk's, and then I conjugate that, so it's the sum of the xk's minus jyk's. Now I can split the two sums up. This is the sum of xk minus j times the sum of yk's. The j's are constant in each of these. Well, let's just do it in this step first. I can do that. We have the sum of the minus jyk's, but I can pull the j out because it's a constant with respect to the summation. So I'll write it that fashion. But this now becomes the sum of xk plus j sum yk conjugate. Just using the properties definition of conjugate. The sum of this is the real part, this is the imaginary part, so the conjugate, this can be written as this conjugate. I just flipped the sign in front of the j. So that's the conjugate, and now this becomes nothing more than the sum of the zk conjugate. So that's what I have here. We started out with the sum of zk conjugate, and we end up with the sum of zk conjugated. So that's the other property. In this step, I took an extra, I skipped a step. What we could do here, this could be written as the sum of xk plus jyk, and then this whole thing is conjugated. But this then by definition is, this here is zk's. So that's what I have here. Okay, so we have our three properties. Now we'll go ahead and prove the theory, the theorem there. All right, so what we want to do is we first start with this, and we want to end up with this here to show that if z1 is a solution to the polynomial equation p sub n is equal to 0, then its conjugate also solves the equation. Let's consider, I'm going to do this in the red color here. Let's consider Pn of z1. Okay, z1 we know solves the equation. So this is the sum of our ak coefficients, z1 raised to the k power, k equals 0 to n. We know that to be true because we've assumed that z1 is a solution to this polynomial equation. Now, let's look at, how about if we put its conjugate into the equation? We want to know if the equation will be satisfied. That is, will this result give us 0? So now what we'll do is put this in the summation form. This is the sum of k equals 0 to n of our ak's, and we have z1 conjugate raised to the k power. Now from this property here, z1 to the k, I can write it as z to the k conjugated. So we'll write this as a sum, k equals 0 to n of ak z1 to the k conjugated, just using this property here. I've just interchanged the conjugation and power. Now the key point here is that a real number is its own conjugate. As I stated before, that if you have any real number, it is also its own conjugate because there are no real parts. So I can write this as sum k equals 0 to n of a k conjugate. The ak's are real, so ak and ak conjugate are identically equal. That's the key point to this proof. Now I'm going to use the second property. I have the product of two conjugates, so I can take the conjugate of the products. So I'll write this as the sum k equals 0 to n ak z1 to the k, and that is conjugated. That's using that property. Now let's rewrite this. We have the sum, I'll just rewrite it here, sum of k equals 0 to n of ak z1 to the k, and that's conjugated. But now using this property, where at this I can bring the conjugation outside the sum. So this is the sum of k equals 0 to n of ak z1 to the k, and that whole sum is conjugated. We're using this property. Well, what is this? This was our original proposition right here. This is equal to 0. this is identically equal to 0. So this is 0 conjugate, which is 0. So we've proven that if z1 solves the polynomial equation with real coefficients, its conjugate also satisfies the equation. So thus it is proven. If z1 is a root, z1 conjugate is also a root.